All right, so here we are with worksheet number 8. Well, right now you're looking at the blank iPad, but I'm just going to talk about our equation sheet that's on the first page of worksheet number 8. This is covering magnetic flux, Faraday's, and motional EMF. And this is going to be a review and extension of what we reviewed last week. And again, this is to get us on pace where SI is 1 week behind lecture. Okay, so magnetic flux. Basically, it's just a magnetic field when it's penetrating a loop of a certain area, A. You can calculate the magnetic flux is equal to that magnitude of the constant magnetic field times the area. And it's a dot product. A dot product means you can either be a cross product where it's sine and the angle between your two vectors, or a dot product where it's your two vectors and then times the cosine angle. So it's kind of weird, right? Like, what's an area vector? Well, the area vector is going to be perpendicular, so it's going to be pointing straight up, right? So normally your angle between B and A is 0, cosine 0 equals 1, so you don't really worry about it. And then by kind of relation, when we talk about a cross product, that's a sine and then an angle, and you notice that the sine is normally 90, and that's 1, so you don't normally worry about it. But just to keep in your back pocket. Faraday's law, this tells that a change in magnetic flux will result in an induced current. So we have N as the number of loops. We have the magnetic flux divided by the change in time. And what are the ways to create an induced voltage or EMF, right? It can occur by 3 different ways. You can either change the strength of the magnetic field. You can change the area that encompasses the flux. So like expand the loop or lessen the loop's diameter. Or you can change the orientation of the loop. So typically you'll see that the loop is, it's either going to be like, let's say it's standing straight up, but if you rotate it onto an angle, different amount of B field will be penetrating, so you can treat it differently. And then Lenz's law. This is kind of the tricky point of this. And basically it tells us that an induced current flows in the direction that produces a magnetic field that opposes a change in magnetic flux. I'll discuss this more in a sec. And finally, we have motional EMF. And this is an equation that we can use in special cases. And that's going to be when we have increasing or decreasing magnetic flux in the shape of a square or rectangle. So when you see a square or a rectangle, or let's say like a rod rectangle moving through an area with a magnetic field, think this BLV equation. And something I want to bring attention to is this negative sign that you see in front of Faraday's law and in front of this motional EMF equation. And also, like, if you have a good eye, you can see how motional EMF is derived from the Faraday's law equation. But just recognizing that you can use that in the special cases that I've already discussed can kind of skip you that derivation process. Okay, that negative sign is less to tell you like the sign is negative or positive. It's to tell you that it's increasing or decreasing, right? So you don't really have to worry about that negative sign. Like sometimes, unless like, given the context of the question, I'll say. So now back to Lenz's law. So this law states that an induced current will flow in a direction that opposes a change in magnetic field that produces it. So basically, if you have a magnetic field that's increasing, the induced current will flow in a direction such that it produces a magnetic field that opposes that increase, right? So remember, with our right-hand rule number 2, based on the direction of the current, our thumb, we can get the direction of a produced magnetic field. That direction of the produced magnetic field will oppose the direction in which the magnetic field is like increasing, given the parameters of the question. Okay, and then by inverse, if the magnetic field is decreasing, the induced current will flow in a direction that produces a magnetic field that opposes that decrease. So you can either think about it that way and use right-hand rule number 2, or you can do what we did previous session, where I'm not going to go through each scenario, but where you increase the amount of field going in by Lenz's law to oppose that change. You need to increase the amount of field going out. The only way you can increase the amount of field going out is if you have a clockwise induced current, because clockwise it's going to be pointing out. Okay, so that was word soup. I'll pause the recording and take any questions on this. All right, I think I misspoke. So if you have more B field going in, you need to oppose that by having more or you can oppose that change in field by having an induced current that flows in a direction that you have more going out. And the only way for that to occur is if you have a counterclockwise induced current. I think I said clockwise, I was told. So it's counterclockwise in that scenario. All right, let's do it. Okay, so question 1. Part A, we're asked to determine the induced EMF. Okay, so here we have a motional kind of rod situation. We should know to think in the equation that the induced EMF is equal to that BLV, right? And then each one of those variables is something that's known, so we can just plug in and then work pretty easily here. The next thing we're asked to determine the direction and the value of the induced current. Well, this is actually something I forgot to tell you guys, but the resistance through the rod, or yeah, the rod is 0.5 ohms, so that should make this a lot easier. And then the second thing is when we set up this equation, we know Ohm's law, V equals IR, and we know how to relate that now to the induced EMF. So that induced EMF is equal to the flux times the resistance. Now all we need to do is rearrange to solve for induced EMF. Everything else is a known value. You plug everything in, and you get 0.5 amps. Now, the question of which way the induced current goes, well, you have to ask yourself this. As this rod moves this way, we're going to have more going in. And to oppose that change, we need to have more going out. Because it's more going out, if you either memorize the table that I taught you before, you'll know that's counterclockwise. Or if you think about it, the only way to have, when your finger is pointing counterclockwise for the direction of the induced current, when you put your thumb the direction the current's going, let's say your thumb through the rod, and that's your thumb right there, your fingers will curl up this way. That's why you're going out of the page, and that's why counterclockwise. And this is counterclockwise. So counterclockwise. And then in part C, we're asked for the power generated by the induced EMF. Our equation for power, there's many, but in this case, we're going to use PI squared times R, plug in everything, and we are left with 0.125 watts. Okay, and then now part D, this is kind of a qualitative thing. We want to determine the power, or the power produced by the induced EMF is determined by what? Well, when we have a conductor or a loop that experiences an induced EMF, a current is generated in the wire, and that's due to the electrons caused by the EMF. And this current, in turn, can then be used to generate work, and that can be work that lights a light bulb, powers a smoothie machine, whatever. And then the power produced by the EMF is then determined by the strength of the magnetic field and the rate at which the magnetic field changes. And you can think about that as a conservation of energy, right? It's an extension of that. So what's it determined by? That's the strength of the magnetic field and the rate that the magnetic field changes by. So to illustrate that, the greater the strength of the magnetic field, the faster the rate of change, the greater the induced EMF would be, and the greater amount of power produced would be. Okay, so I'll pause and take questions. Okay, so question 2 is one I'm going to drive alone here. And the reason I included it on this sheet is because it's a special case. And by special case, I mean, given the conditions that this question exists, we have to solve it using kind of a unique setup. So how we do that is, I kind of just revealed the answer right there, but we have this rod and it's between these two resistors. And it can actually be treated as a battery, that being the rod, because it creates an induced EMF on both sides. So then in part A, when we're asked to solve for the current through R1 and R2, we can redraw this whole thing, this is B, we can redraw this whole thing as something that seems a little bit more familiar. Okay. It should remind you now of Kirchhoff's kind of rule here. So in part A, we're asked to determine the resistors, or the current through each resistors. That should be very familiar to what we've done before. And all we have to do is set up the direction of our currents. Let's call that I1. Let's call this I2. And we'll have I3 moving through the induced EMF that's acting on both sides. We'll call that I3. The first thing we need to do is actually solve for that induced EMF. Well, we know what the B field is, that's given. We know what the length is given, and we know the velocity. So we can use that motional EMF equation, and we can get 12.15 volts. And now we're treating that as what it would be for the battery. So first, our junction rule, I1 plus I3 is equal to I2. And then our loop rule, let's start with this loop right here. Oops. Start behind the battery, goes the same direction as our arrow, positive. and then the direction of the current and the direction of the loop bump into each other. And so we call it plus 4, what's the current there? I1. And then now you can just solve for I1. I1 is going to be equal to minus 3.04 amps. Okay, well, our guess is wrong, but we've already talked about this before, how the guess being wrong doesn't really matter as long as you're consistent. And now we can solve for I2 because we already know what I1 is. So our second loop here, same setup where we start. Now our direction of the loop and the direction of the current through R1 are the same. So minus 4 I1. And then we go, same logic applies to R2. So minus 8 I2. Oh, we already know what I1 is, so we can plug that in. Solve for I2. I2 is going to be equal to 1.52 amps. Okay. Moving on to part B, we're asked for the total power. So the total power includes those that both go through resistor 1 and resistor 2. So we're going to have to add those two, plug in. And in this case, you're going to want to plug in the absolute value of I1. And that's just because, there's no true negative current in this case. Rather, it was because our guess is wrong. So you just make sure you plug in the positive. You end up getting 55.36 watts. That's our total power. And then moving on to part C. So part C kind of where it steps up a little bit. And we can redraw our rod. And through our rod, we determine that the direction of the current is going to be moving as such. We'll call that I3. We know how long the rod is. We'll call that L. And we know how the B field is on both sides. It's going into the page on both sides. Am I missing anything? Oh, yeah. It also has velocity going this way. And if you do right-hand rule number 1, where your pointer finger is pointing the direction of the current, I3, your middle finger is pointing the direction of B going into the page, and your thumb is pointing the direction of the force, you'll see you have FB pointing leftwards. And then therefore, to keep that rod at equilibrium, the necessary direction and magnitude would be the force pointing rightwards. And to solve for the magnitude, we can use Newton's second law. And because equilibrium, the acceleration is 0. Our force is acting here. We can draw a coordinate system. F minus FB is equal to 0. We can now solve for this force through the expression of FB. FB is equal to I3 L cross B. It's going to be 90 degrees, so we don't really have to worry about that. I3 LB. To solve for I3, you have to rearrange our loop equation, and we can rearrange our loop equation to equal I2 minus I1. That is going to be equal to 4.56. You know what the length is. You know what the B field is. We now know what I3 is. You can solve for that force as 9.25 watts. And then I'm going to say right words. Okay, so again, I included this question to just kind of highlight this point where when we have these two segments on either side and we have this rod in the middle, it can be treated as a battery. So that's something to just be mindful of. Okay, pause this and okay, let me just add this one thing and write it down here. So creating a battery with an induced EMF, I just said this. By doing so, the voltage can be induced across both the conductor, and that creates an electrical current that can deliver power. All right, so here we have a drawing where we have a metal rod, mass M, slides down a frictionless ramp containing a magnetic field. The ramp has an incline of theta with respect to the ground, and a uniform magnetic field is directed upwards perpendicular to the ground through which the bar moves. Assuming constant speed, find V. Okay, so with this one, it's easiest to reorient the drawing like this. And because we have something with mass, we know there's multiple forces acting here. We know there's the force of, oops, the iPad dropped, sorry. We have, the force of gravity pointing downwards. We have a normal force perpendicular to the ramp. And we also have, a magnetic force, right? We have a rod moving through a magnetic field. So how can we figure out which way that's going? I think with that, it's actually kind of easier to draw it this way again. Okay, so the B field is kind of projecting straight out going this way. As your rod is moving along this, down this frictionless ramp going this way, What's happening within this space? Well, you're having less magnetic field going out. And then because we have less going out, to oppose this change by Lenz's law, we need to have more going out. Because of more going out, the only way to have more going out, right-hand rule number 2, is to have our fingers pointing upwards, going out of the page. Therefore, you will have a counterclockwise induced current. And now if we look at the cross section, that is this diagram here, that means our current is pointing straight into the page, right? So if you put your finger going straight into the page, our middle finger pointing up the direction that the field is going, our thumb points towards the east or rightward. So therefore, we have a FB pointing directly rightward, like this. Okay? And with a question like this, we know that the entire acceleration is being contributed by the x direction. So when we draw our coordinate system, it's actually easiest to draw one that mirrors the directions of the ramp. So we have our coordinate system, but it's on an angle, it's theta degrees with respect to the x. Okay, so now because of this, we need to break our forces into their components where necessary. So that includes the force by gravity. And again, the angle here is theta. And that includes FB also, which is now going to need to be broken to its components like this. And again, our angle theta is right here. Okay, so we can repeat that angle theta everywhere. And now we need to solve for the forces that are acting here. Starting in the x direction, well, only in the x direction, we know that it's going to go to a constant speed, acceleration is equal to 0. What are our forces acting in the x direction? Well, we have a sine component of the mg, and we have a cosine component of FB. So mg sine theta minus FB cosine theta is equal to 0. Let's clean this up. And now let's expand what FB is equal to. That's going to be equal to I induced LB. And then sine theta, but we know the angle between them is equal to 0. So then 1. So I'm just going to exclude that, cosine theta. But we don't know what I induced is, but we do know how to find that. And again, that's our motional EMF. E induced is equal to I induced R. Okay, rearrange. Oops. Okay, plug everything in. And actually, if you have a good eye, you can see we can simplify this more. Because when we have motional EMF, what does this E induced equal? Well, E induced is equal to BLV cosine theta. So now we can substitute that back in. And you're going to see now that we're going to have a few squared terms here. And that's going to be equal to mg sine theta. And what we're looking for is that V, which is embedded in here. Rearrange a little bit, clean this up. We're going to have mg r sine theta divided by b squared L squared cosine squared theta is equal to V. Bam. That's how you do that one. All right. And that's it for the recording. Thanks for watching.